So what I want to do for the last half hour now is just focus on a particular type of equilibrium, and it's one that for some reason we do to death. I don't know why, because it's really just an exercise in maths. But nonetheless, we do it at school, you're going to do it in first semester, you're probably going to do it in second year chemistry if you hang around and do the right sorts of papers. We're going to go back and talk about these dissolution reactions that we did right at the start. Okay? And so right at the start of today, we looked at this reaction. Sodium chloride, an ionic solid, you put it in water, it doesn't react with the water, it dissolves in the water to give you sodium ions and chloride ions. And we said that this reaction goes to completion. So if you have a certain amount of salt and you stick it in the water, that dissolution reaction is going to keep happening until all the solid salt is gone. And so we say that that reaction has gone to completion. However, there are also many examples where the compound does not completely dissolve. And so you'll have an ionic solid and you'll put it in water and it will dissolve a bit, but then it will stop. And you can't dissolve any more. And so these get this name sparingly soluble compounds. So these are ones that only dissolve a little bit. Okay, so we're going to use as our example here, again, we were horribly unimaginative and talked about NO2 and N2O4. For this we're going to talk about silver chloride, which is equally as unimaginative, but there it is. So silver chloride is an ionic compound. It's made up of a silver plus cation and a chloride anion. And if you take a bit of solid silver chloride and you stick it in water, then it will dissolve a little bit. And when it does dissolve, you will get silver ions and you will get chloride ions. But it only dissolves a little bit, and then it will no longer appear to be dissolving because it reaches an equilibrium. In this case, an equilibrium between the dissolved ions and the undissolved solid. Right? So it's a little bit different to the one we were talking about before. Now you've got an equilibrium between a solid and the dissolved ions. And what you will find if you go in and you measure the concentrations of these ions by some experiment is that the equilibrium position lies very much to the left-hand side. So in other words, the vast majority of silver chloride molecules stay as solid silver chloride, and only a very small proportion of them dissolve before you reach equilibrium. Because it's an equilibrium, we can write an equilibrium constant expression for this equilibrium, but it's going to be a little bit different to the ones we've seen earlier because, of course, all of the reactants in this case are solids. There's only one reactant, and it's a solid, and so you don't put solids in. And so the equilibrium constant expression for these sorts of equilibria is quite a lot more simple than the ones that we've already seen. Okay, so this is what it's going to look like. Here's your equilibrium again, AgCl, solid in equilibrium with the ions. And so the K is just going to be this, right? Normally it's concentrations of products raised to their stoichiometric powers divided by concentrations of reactants raised to theirs. But now the reactant is a solid, so that means there's nothing on the bottom of your expression. There's only the products there. And so the K is just going to be the concentration of the silver ions at equilibrium times the concentration of the chloride ions at equilibrium, right? And that's it. And we give this a name, and again, this kind of is a bit like quotient. It's relying on mathsy words. But if you think about it, you get the K by working out the concentrations of those two ions and multiplying them together. And when you multiply two things together, what you get is the product, yeah, to use the mathsy language. And so this K has given a special name. It's called the solubility product. So product because it's what you get from multiplying those concentrations together. And as we're going to see, we can also, another word for those concentrations is the solubilities of the solid. Right? So we're getting back to that. Now this is called Ks in NCEA. At university we call this KSP, SP for solubility product. Yeah? It's the same thing though. And so correctly then we can write KSP equals the concentration of silver ions at equilibrium times the concentration of chloride ions at equilibrium. Okay, so this idea that we've got K but then SP to specify a particular type of equilibrium is something we're going to see a lot, because we come across equilibria in all sorts of different areas of chemistry, and each time we do, we tend to give the K a different little subscript. So you're going to see Kas, and you're going to see Kbs, and you're going to see Kws, and Kc, and Kp, and this one's Ksp, right? So that tells you that it's Ksp is what you would write for an equilibrium involving a sparingly soluble solid kind of dissolving to give its ions. Yeah? Ka is for a different sort of equilibrium, Kb is for a different sort of equilibrium again. Okay. Now, you can go look this up in a book, because again, someone's already worked this out, because it's a constant, so it doesn't matter how you do the reaction, so long as you do it at this particular temperature, you're always going to get the same answer. And so someone's done this, and they've worked out the value for the Ksp for silver chloride is 1.8 times 10 to the negative 10. So that's a little number, right? And remember, little numbers indicate that the reaction position of equilibrium lies very much on the side of the reactants. So most of the stuff is still reactants when it reaches equilibrium, and only a very small amount turns into products. So those concentrations of those ions are small. So this very small number indicates the concentration of the ions at equilibrium is very low. How low? Well, what we can do is we can work that out. And we can work it out by recognizing that if we look at our balanced chemical equation to describe this equilibrium, we see that one lot of silver chloride, when it does dissolve, doesn't very often, but when it does, you get one lot of silver ions and one lot of chloride ions. So 1 to 1 to 1 stoichiometry. So that means that whatever the concentration of the silver ions is at equilibrium, the concentration of the chloride ions must be the same. Yeah? Every time one lot of silver chloride dissolves, you get one silver ion and you get one chloride ion. So their concentrations in your solution must be the same as each other. If we give this concentration, so we've said that the concentration of the silver ions is going to be the same as the concentration of the chloride ions, right? And that follows from the balancing of the balanced chemical equation, the 1 to 1 to 1 mole ratios. Let's imagine that we're going to call that concentration of the silver ions, whatever it is, we're going to give it a symbol S. So we're going to do like algebra. We could call it X, the unknown thing, but we're going to call it S. S for solubility. Then what we do is we can rewrite our Ksp expression, and instead of writing concentration of silver plus ions at equilibrium, which is a number, which we don't know, so this is a symbolic way of representing a number, we're going to change that into a different way of symbolically representing that number, and we're going to call it S. Right? This is purely an exercise in mathematics. So it is designed to confuse you. Yeah? But this is the way it's done, and you're going to see it again in first semester, so you need to be okay with it, because we always ask you about this stuff in exams. Yeah? So instead of writing concentration of silver plus at equilibrium, we write S. Both of these refer to the same number. It's just a different way of writing it down. Yeah? And because the concentration of silver ions in this particular equilibrium reaction will be the same as the concentration of the chloride ions, we can write an S for that as well. Because whatever this number is, it's the same as that number. And so if this is representing that number, then this is going to be representing that number, and they're both S as well. Does that make sense? Yeah? I sometimes worry this is too simple and people get confused because they think it's harder than it really is. So all we're doing is writing something that looks like chemistry to writing something that looks like maths. Right? And then because these two are the same, instead of writing S times S, we can write S squared. Because mathematically those are the same thing. Yeah? And so instead of writing KSP equals the concentration of silver ions at equilibrium times the concentration of chloride ions at equilibrium, we can say KSP equals S squared. Purely for algebra's sake. Yeah?
If, say, Ag wasn't the same concentration as Cl,
Yes.
what would you label that like S1 and S2?
We're going to get to that. Yeah. So we can say that the KSP is equal to S squared, and the KSP, of course, is a number, because it's an equilibrium constant, so it's just a number, and the number is 1.8 times 10 to the negative 10. And so it then follows that if S squared is equal to 1.8 times 10 to the negative 10, we can find S by taking the square root of that number. And so we can work out that S, which will correspond to the concentrations of the silver ions and the chloride ions, is equal to 1.34 times 10 to the negative 5 moles per litre. And so there's a few things to note then. One is that you have to be relaxed about this way that we apparently arbitrarily turn chemistry into algebra, right? Because many of you would have seen that this is kind of obvious. If the concentrations are the same, then it's just the square root of the number will give you the concentration. But instead, we go and we jump and turn it all into algebra and then solve it and then jump back again for no apparently good reason. This is the way it's done. I do not like it, and in fact, we have the reason why I'm not going to be here 2 Mondays from now is because I'm going to be in Wellington. We have a meeting every year of all the first year chemistry coordinators to compare notes and see what we're doing and moan about students and stuff like you do. And last year we had one of these meetings, and we were all pretty much came away saying if it was up to us, we'd get rid of all of this entirely because it's nonsense. Right? All of us who actually have to go about teaching this stuff think that this is just an exercise in maths, and KSPs are nothing special, and why are we making such a big deal about it? But this is what we do, so you need to be able to confidently do these problems this way. Right? So we start with chemistry, we turn it into math, and then we get back into chemistry again. Right? And so this is the way, if you're going to do your nice working, you want to do the working to work out what the concentrations of these ions are in this equilibrium solution. You should also note that when, even though the K has no number, once you write the S, it magically gets units back. Right? There's no units for the K, but there is units for S. So we magically make them disappear when we work out the equilibrium constant, and they magically reappear when we use that to work out solubilities. Again, you just have to accept that. Right? But the S represents a concentration, and concentration has units of moles per litre. And then the last thing, and this is just so that you're aware if you see it, doing that square root sign in Word is not straightforward, whereas taking that number and writing it to the power of 1/2 is much easier. Mathematically, those are the same things. So you need to be aware that if we write 1.8 times 10 to the negative 10 to the power of 1/2, that's just another way of saying the square root of that number. Okay? Right. So that's how you would do a KSP calculation for this. And if we gave you the concentrations of the silver ions and the chloride ions, you could work out the KSP. And if we give you the KSP, then you can do this calculation and work out the concentrations. Yeah? Right. And so we call S the solubility of silver chloride. And this was why, because you work out the KSP by multiplying the S's together, this is why KSP is called the solubility product. It's the product of the solubilities, which are symbolized by S, but which mean the concentrations of the ions. Note that the solubility of silver chloride, this number we've just worked out, represents the maximum concentration of ions that can be obtained in the solution. Right? You stick your lump of solid silver chloride in your water and you stir it up and you let it reach equilibrium, and once those concentrations of those ions reach 1.34 times 10 to the negative 5 moles per litre, that's it. You can't get more silver ions and chloride ions into that solution. You've reached equilibrium unless you heat it up, and then everything changes. You keep the temperature the same, you can't dissolve any more solid in that solution. And so we call the solution saturated. Right? So in other words, you can't fit any more ions into that solution. And then the last little bit there is the bit you probably already know, even if you didn't know any chemistry, you'd kind of know this, is that the KSP, the equilibrium constant for this dissolution process, is dependent on temperature, like all equilibrium constants are. But in this case, what you find is that if you increase the temperature, the KSP will increase. So in other words, if you heat it up, more solid can dissolve before you reach equilibrium. Okay, and that's kind of what you would expect. If you want to make something dissolve more, you heat it up. And there's a nice bit of math to describe how that works, but we're not going to do that here. Okay? Now then, we move on to the slightly more complicated example. So let's look at another type of dissolution process, but now involving calcium carbonate. Okay, so this is calcium carbonate, quartz, limestone, and chalk. Yeah? So if you take a bit of chalk and you stick it in water, then it will dissolve a little bit. Not very much, but a little bit. The KSP for calcium carbonate is 3.3 times 10 to the negative 9. So it's a little bit better than silver chloride, but not by much. What I want to do quickly is go through how we would do the same sort of analysis in terms of working out the solubility of calcium carbonate for this one as we did for the previous one, because there's an important difference here that is the thing which we will always ask you and which you need to be good about. And the difference comes... Oh no, hang on, why am I doing this? Hang on. Don't. No. That's one to do in your own time. Sorry. This is the one I want to do. So you can, given that KSP, you can work out the value of S, yeah? Because calcium carbonate is the same as silver chloride. This is the one that's slightly different. Silver carbonate, right? So the KSP of silver carbonate you're given as being 8.1 times 10 to the negative 12. So what we want to do here is work out the value of the solubility S. And the reason why this one's different is because when we write the equation, the equilibrium equation looks like this. We have solid silver carbonate dissolving to give 2 lots of silver ions and 1 lot of carbonate ions. So it's no longer 1 to 1 to 1 balancing, it's 1 to 2 to 1. If we write the KSP expression for this one, it's going to look like this, right? So because there's a 2 in the balancing, now the KSP looks like this. KSP equals the concentration of the silver ions at equilibrium squared times the concentration of the carbonate ions at equilibrium. So in order to calculate the solubility, first we've got to write down the equation, the solid dissolving to give the ions. Then you write down the KSP expression, which looks like this. And note that the equilibrium concentration of silver plus ions is squared due to the balancing in the equation, right? It's one of our rules. The rules for writing the K are that if there's a 2 in the balancing, we have to square the concentration of that thing in the equilibrium constant expression, right?
So if it's 3, you cube it?
If it's 3, you cube it. If it's 4, you take it to the power of 4. Yeah? You won't see a 4, and you probably, no, you won't really see a 3 either. I mean, you can. There are some compounds where that would be the case, but you're not going to see them. And now we solve for S. And this is where this becomes a bit different to the previous one, because now we have to deal with the fact that the concentration of the silver ions in the solution is not going to be the same as the concentration of the carbonate ions. Right? Because every time 1 mole of silver carbonate dissolves, we get 2 moles of silver ions, but only 1 mole of carbonate ions. And so that means that the concentration of the silver ions will be twice the concentration of carbonate. We don't know what those concentrations are yet, but what we do know is that the concentration of silver will be twice as big as the concentration of carbonate, just from the balancing in that equation. Yeah? And so now if we're going to do our little sidestep and turn everything into algebra, what we have to do is this. We say, let's imagine that the concentration of the carbonate ions is S. And if we do that, that means that the concentration of the silver ions is going to be 2 times S. Okay? S is just representing the concentration of carbonate ions. Whatever that number is, we're going to call that S. So that means that the concentration of silver ions, which is twice as big, we can represent by 2 times S. Yes? We could have said that the concentration of silver ions is S and the concentration of carbonate ions is a half S, if we wanted, but we don't. Well, no one does. They do it this way, so this is what we have to do. So carbonate is going to be S, and so the silver ion concentration will be twice that, because there's twice as much of that in solution due to the way that the equation, that the reaction works. Okay? And so then, now we can say that the concentration of carbonate is S and the concentration of the silver ions is 2S. We put these S's back into our KSP expression, just like we did before. And so we do this. Instead of writing KSP equals the concentration of silver ions at equilibrium squared times the concentration of carbonate, we write that the KSP is equal to 2S, the constant which represents the concentration of silver ions, squared, times S, which represents the concentration of carbonate ions. Sir?
Was that last slide missing a square?
Was it? Nope. Nope. 2S is a number which corresponds to the concentration of silver ions. But that number will be twice as big as the value of the concentration of the carbonate. So if we call the carbonate concentration S, moles per litre, then the silver concentration will be 2 times bigger than that. So 2S moles per litre. Yeah? So no squareds here, but there are squareds here, because now our equilibrium constant expression requires us to square the concentration of the silver ions, because it's the rule. In the same way that there's nothing on the bottom of the KSP expression for the reactant because it's a solid, and there's a rule that says you don't put that in, there's another rule that says that if there's a 2 in the balancing, we have to square the concentration. And so suddenly I'm seeing the usual number of worried faces, the dilemma of the 2 2s. Right? Why do you do it twice? You do it twice because each of the 2s mean different things. This 2 here is telling you that this number, whatever it is twice as big as this number. This 2 is here because it's the rules for writing the equilibrium constant expression. If you don't have them both there, then it won't work. Right? Sir?
For the reason for the why for why we square it, is it just not worth asking why that rule is there? So the reason that we square the concentration of
Yep.
the silver, that rule.
Yep.
We just not understand why we do that.
If you don't square it, there's this thing that regardless of what the concentrations are,
Yeah.
when you do the ratio, the K will always be the same.
Yeah.
Right? If you don't follow all the rules, then the K won't always be the same. Right? So if you decided that we didn't have to square it, then if you took 5 different reactions, 5 different lots of the same reaction, all at equilibrium, and you measured their concentrations and you did the math, the K would be different every time. But if you follow the rules and do the squaring and stuff, then the K will be the same every time. So it will be a constant. Right? So you have to follow the rules, and that means you have to square the silver concentration, which in this case is being represented algebraically by the term 2S. Yeah? I wish this wasn't the end of the second lecture, but this is really important that you get this. And then if you take the 2s and you square that, 2s squared is the same as 4s squared. 2 squared times s squared, so 4s squared. And then that times s is 4s cubed. And so for this type of equilibrium, where you have a solid dissolving to give 2 lots of one ion and 1 lot of the other, then you have this relationship that the KSP is equal to 4 times s cubed. Whereas the previous one, where you had a solid dissolving to give 1 cation and 1 anion, the relationship was KSP equals s squared. Right? So it's different. And it's different because of the way of the balancing in the chemical equation you start with. So we can say then that 4s cubed is equal to the KSP, and the KSP is equal to 8.1 times 10 to the negative 12. And so then we can do some math on that, which looks like this. We can rearrange this for S, and so S is going to be the KSP value divided by 4, and then all of that you cube root, or if you like, you take all of that to the power of 1/3. So that's calculator stuff, yeah? And then you can work out the value of S, which corresponds to the concentration of the carbonate, and will be half the value for the concentration of the silver ions. Now, in theory, we could do things like this. We could do what we do. Calcium phosphate. Which is that. And that would form an equilibrium with 3 lots of calcium 2+ ions and 2 lots of phosphate ions. And then it's going to be 9s cubed times 4s squared, which is 36s to the 5. And then it all gets very complicated. Exactly the same thing, the only difference is the math. But we're not going to ask you crazy ones like this, all right? The only ones you're going to see are the same ones that they would have shown you at school if you've done this at school, which is that the KSP is equal to s squared, or KSP equals 4s cubed. Right? So you have these 2 different types of equilibria, which depend on how the ionic solid you start with is put together. But we're only going to worry about those 2 different types here, even though there are other possibilities.